This week, we'll be using the counting principle. We'll also be using permutations and combinations to find the number of events that something has. The fundamental counting principle. The most important of these is the fundamental counting principle. The fundamental counting principle says that e sub 1 and e sub 2 be two events. The first event, e sub 1, can occur in m1 different ways, and e sub 1 has occurred. E sub 2 can occur in m2 different ways. The number of ways that the two events can occur is m1 times m2, which now I'll put it into English. What they're saying is, if you have, let's say we have a dice, okay? Let me change my marker here. Let's say I have a dice. Let's see if I can draw this halfway decent. 6 sides. You know, maybe this is 1 and 2 and a 3, and then we have a coin. And we want to know how many different ways that this, if I toss a dice and I toss a coin, how many different outcomes are there? Well, the fundamental counting principle says, how many are there on a dice? Well, there's 6. How many of them are on the coin? Well, there's 2. So if I just multiply that together, 6 times 2 is 12. So that means there's 12 different ways that this can occur. Now, I could write them all out. You could get a 1 on the dice and a head on the coin, a 1 on the dice and a tail on the head on the coin. 2 heads, 2 tails, 3 heads, 3 tails, 4 heads, 4 tails, 5 heads, 5 tails, and 6 head and 6 tails. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 different things. This is called a sample space. If you write it all out, it's called a sample space. Most times we don't want to write it all out because, you know, what if they said you have 3 dice and you're going to shake all 3 dice? What are all the different combinations you can have of the 3 dice ending up? Well, you'd end up with 6 times 6 times 6 because there's 6 possibilities on the first, 6 on the second, 6 on the third. I would not want to write that sample space out. I mean, I could start, you know, 1, 1, 1. You could have all ones. You could have 1, 2, 1, 1, 1, 2. You could have, and there's, what is 6 times 6 times 6? Well, 6 times 6 times 6 would be 216. So I'd have 216 different things in my sample space. Ooh, I would not want to write that out. That would take me quite some time to do. So the fundamental counting principle says all you have to do is multiply the number of ways the first event can happen and the number of ways the second event can happen. That's it. How many different pairs of letters from the English alphabet are possible? Okay, well, there's 26, right? There are how many different pairs? Okay, so what they're saying is you could have AA, AB, AC, AD. How many different ones are there? Well, when you think about it, there's 26 letters in the alphabet, 26 times 26, because you're dealing with 2 different letters. So there would be 776 different ways that could end up. Again, another sample space I would not want to try to figure out. It would take me a long time. Here's an example. It says a high school cafeteria. Diners can choose 1 vegetable from a choice of 5 vegetables, 1 meat from a choice of 2 meats, 1 serving of bread from among 2 different types of breads, and dessert from among 3 different desserts. How many meal configurations are there? Well, 5 choices for vegetables times 2 choices for meat times 2 choices for bread times 3 different desserts. 5 times 2 is 10 times 2 is 20 times 3 is 60. So there's 60 different possibilities that you could have there. This is the fundamental counting principle. There are 13 patients in Dr. Ziegler's waiting room. Dr. Ziegler can see 5 patients before lunch. In how many different orders can Dr. Ziegler see the 5 patients? Well, when you think about it, this is a fundamental counting principle also. You can see 5 patients. Well, the first, he could see 13 different ones, right? Because there's 13 patients there. And then there's only 12 left, then 11, then 10, then 9. So really, 13 times 12 times 11 times 10 times 9 is 154,440. That's a lot of different ways you could see those patients. But using the fundamental counting principle. Super simple to come up with the total number. Now, we wouldn't want to do a sample space there. That would take forever. All right, so that's the fundamental counting principle for this week. The second thing we're going to work on this week is permutations. What is a permutation? One important application of fundamental counting principle is in determining the number of ways that n elements can be arranged in order. An ordering of n elements is called a permutation of the elements. So the definition of permutation, a permutation of n different elements is an ordering of the elements such that one element is first, one is second, one is third, and so on. How many permutations of the letter A, B, C, D, E, and F are possible? Well, when you think about it, there's 1, 2, 3, 4, 5, 6 different letters. So 1, 2, 3, 4, 5, 6. So how many ways can I put a letter here? 6. Then one of the letters is being used here, so there's only 5 letters left. 4, 3, 2, 1. 6 times 5 times 4 times 3 times 2 times 1. Now, some of you might know an easier way of writing that. It's called 6 factorial. This factorial sign means that, like if I said 8 factorial, well, that's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And factorial just means that you just keep multiplying all the way down to 1. Okay? And your calculator should have a factorial button on it. So the number of choices for the 6 positions are as follows: 6, 5, 4, 3, 2, 1, or 720 and 6 factorial. Number of permutations of n elements, number of permutation of n elements is n times n minus 1 times so it's just n factorial. So an easy way of writing it is just n factorial. Now let's say that we have permutations and you only want a portion of them, like that last problem that we did with the doctor's office, that there were 13 people in the office, or 13 people in the office. You can only see 5 before lunch. Well, that would be 13 permutate 5. So that would be, we'd write this 13 permutate 5. This is the 13, this is the 5, okay, because you're only taking them. So you would just put 13 factorial in there over n minus r factorial, and you would get your answer. Well, 13 factorial, we'll leave that on top, over n minus r. Well, the n is 5, or I'm sorry, n minus r, so that's going to be 13 minus 5, which is, what is that, 9? No, 8. 8 factorial. So 13, and then this is where it gets cool, because learning how to work with factorials is awesome. So you could write it as 13 times 12 times 11 times 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. But guess what? On the bottom, you have 8 factorial, 8, 7, 6, 5, 4, 3, 2, 1. So all of those are going to cross off. So you're just left with 13 times 12 times 11 times 10 times 9 times 8, which is exactly what we had the last time. So when you're dealing with factorials, like if you had something like 10 factorial over 5 factorial, guess what? You could write it all out, but what does this really equal? It just equals 10 times 9 times 8 times 7 times 6, because the 5, 4, 3, 2, 1 is going to cross off with this 5, 4, 3, 2, 1. So this is the formula that you use to find permutations. The number of ways, if you had 13 people and you're going to choose 5 of them, this is the way. Okay? And this is called a permutation. Remember that permutations, order is important. Okay? This is really, really important. I always mess this up. I always get them opposite because we have combinations coming up next. Order is important. And what does that mean? Okay, so for example, A, B, C, D, if you have the letters A, B, C, D, and you want to take 3 at a time, you can count permutations A, B, D, and B, A, D as different because the order of the elements is different. Okay? I always tell kids that when you have something, when order matters, like for example, if you had 3 people, let's say we had Jim, Bill, and Sue, and they were all in a race, and you got let's say $1,000 for first place. You got $500 for second place, and third place you got $50. Doesn't matter if Jim came in first, Bill came in second, and Sue came in third, or is this the same thing? And lo and behold, this is not the same thing. So in this problem, order is important. Jim, Bill, Sue is not the same thing as Sue, Bill, Jill. Okay. Now, when order does not matter, okay, when order is not important, okay, then we use what is called combinations. Okay, and that's the next thing coming up. Okay, so permutations is distinct objects. So to find the distinguishable permutations, we use this. Combinations is when order doesn't matter. Okay. So when isn't order important? Well, let's say you go to Pizza Hut and you went up to the counter and you ordered your pizza and you said, okay, I want ham, I want pineapples, and I want green peppers. Okay. All right. And then they go back and they start making your pizza, and you go up to the counter and you say, no, 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 no. I want green peppers, ham, and pineapple. Well, do they have to redo the pizza? No, because order in this problem doesn't make any difference. Ham, pineapple, green peppers is exactly the same thing as green peppers, ham, and pineapple. Okay. So when order doesn't matter, we use combinations. And the formula for combinations is a little bit trickier. Okay. And that is, oops, I thought I had the formula. Oh, here it is. The formula is n factorial over n minus r factorial, which is exactly the same thing as the permutation one, except then you divide through by r factorial also, which what that does is it cuts out all the extras, okay, the ones that overlap. So it's very similar. The two formulas are almost identical, except you have that r factorial on combinations. So an example is, so if I asked you to find 5 combination 3, well, remember the formula is, let me get my pen's not working here, n factorial over n minus r factorial times r factorial. Okay, so n is always the largest number, so that's 5 factorial. And then 5 minus 3, so that's 2 factorial, times r factorial, so that's 3 factorial. You cannot multiply factorials together, okay? So this does not equal 6 factorial. So if I was going to solve this, I'd go 5 times 4 times 3 times 2 times 1. Well, on the bottom, I have 3 factorial, so 3 times 2 times 1. That crosses out all that. And then I still have this 2 factorial, which is just 2 times 1. Well, I can simplify 2 into 4. So 5 times 2 is 10. So my answer is just 10. So you should be able to use combinations, the formula to find combinations and permutations. Okay. All right. So here's an example. It says 9 weightlifters are competing in a deadlift competition. In how many ways can the weightlifters finish first, second, and third? Okay. So that means I have 9. So this is a combination problem. Why is it a combination? Because it matters or order is important in this one. So 9 weightlifters in a deadlift. How many ways can the weightlifters finish first, second, and third? No ties. This is a permutation because order does matter. Okay, so I'm going to do permutation. I'm going to do 9 permutate. What was it? 3 places. So I've got first, second, and third. So now that's just n factorial over n minus r factorial. So I've got 9 factorial over 9 minus 3, so that's 6 factorial. So that's going to end up being 9 times 8 times 7, right? Because the 6, all that goes down. So 9 times 8 times 7 should be 504. Right there. All right. Hope to see you guys on Monday at the main lesson. You guys have a great week. Bye.